So in this video, I'm going to do my best to show you molecular shapes. I've got model kits here that if we were in the classroom, obviously you'd be able to look at them and touch them and so forth. But we got to do what we can. Later on in next week, I guess you'll be able to use these computer simulation to kind of visualize the models as well. So let's get started. We've got to talk about VSEPR theory, how we predict molecular shapes and molecular polarity. You spent some time last year learning how to do this. We're going to expand on that idea because now that you know we can go beyond an octet, things can have 5 bonds and 6 bonds, you're going to see that. So let's get started. So again, we're using VSEPR theory to predict the shapes of molecules. VSEPR stands for valence shell electron pair repulsion. So the idea is that electrons are going to repel each other because they're all negatively charged. So orbitals, when things start to bond, orbitals are going to try and be as far apart from each other as possible. That includes lone pairs and that includes bonding orbitals. So that's the idea, the big idea behind VSEPR theory. The number of domains is going to dictate what kind of shape you wind up with. So when I say an electron domain, I mean a couple of different things. You could have a lone pair of electrons. So for example, on this structure, I'm representing a lone pair just with a small little white atom or piece of plastic, really. You can have a single bond where you're sharing one pair of electrons. Okay, so there's a single bond between the black and the green. Or one domain is represented by a double bond or by a triple bond. Okay, so here's a triple bond, one domain. Here's a double bond, one domain. So in this structure, I have the 3 different kinds of domains. I've got a single bond, I've got a double bond, and I've got a lone pair. There are a total of 3 domains in this structure. So the number of domains is going to dictate what shape you get. Obviously, the more domains you have, the smaller the angles of separation become. So you've learned the first 3 last year, the linear domain. So I made this very simply. If you have 2 domains, you wind up with a linear molecule. Obviously, one domain is linear as well. So ignore the fact that there's holes there. They didn't give me anything in the model kit that has just a 180-degree 2 bonds. So here is an example of 2 domains. They are going to be 180 degrees apart. So you're going to wind up with a linear molecule. Things get a little bit more exciting when you get into 3 domains. Now we have a flat structure that is 120-degree separation between the 3 domains. That's as far apart as you can get 3 things. If we move on to 4 domains, you get that tetrahedral shape that we saw so often last year. Okay, now we're down to 109.5 degrees, and yes, you need to know bond angles. So that's something that AP frequently talks about. So there's our 4 domains. You can get 4 things 109.5 degrees apart. And now the new ones, 5 domains. This is called trigonal bipyramidal. So if you notice on the equatorial, so we typically hold it like this. So if I rotate it, you can see that in the equator, the center part, there are 3 that are 120 degrees apart from each other. It's hard. There we go. 120 degrees apart. Okay, so those are the equatorial atoms or bonds. And then we have the axial, which are the verticals. Okay, so we have 120 degrees between the different equatorials. We have 90 degrees between the axial and the equatorial. There's a total of 5 domains. So I've got 1 3-sided triangle coming from the top. I've got 1 3-sided triangle coming from the bottom. So trigonal bipyramidal is the shape that you wind up with 5 domains. And then 6 domains, everything's 90 degrees. No matter how you turn it, all looks the same. It is called octahedral because it's a 8-sided figure. 1, 2, 3, 4, and then 5, 6, 7, 8. So it's an 8-sided figure, so it's called an octahedron, and you can see it very nicely in this picture. Okay, so these are the shapes of the electron domains. This is the electron geometry that we're looking at. How many domains do you have? The molecular shape is going to depend upon how many of those domains are actually bonding. So like in this one, we've got 3 bonding, but I got 1 non-bonding domain. So total of 4 domains, but they're not all bonding domains. So we're going to talk about how we get those different shapes and what words we use to describe the more complicated ones. All right, so each set of electrons occupies a position around the central atom. Okay, that represents the electron geometry. The number of domains around the central atom is the electron geometry. But if there are lone pairs, which are essentially transparent when you're thinking about the shape of the molecule themselves, like where are the actual atoms, lone pairs aren't an atom. They don't represent an angle, essentially. So the lone pairs may be present and are part of the electron geometry, but they are not part of the molecular geometry. So even though they're invisible, the lone pairs are going to make their presence known by distorting the positions of the bonds around them. Okay, so lone pairs are going to repel the electrons in bonds. So this is going to result then in something called molecular geometry. So we've got these essentially five electron geometries, what you saw on the last slide. But there are subcategories under each of those electron geometries that describes the molecular geometry. So of those electron domains, how many of them are bonding domains? That's the idea. So in a linear molecule, it's pretty easy. 2 electron domains. You've got something that's linear, and you can get that a couple different ways. By adding just single bonds, so like the BeH2 or whatever this one is. But you can also get linear molecules when you have doubles or 1 single and 1 triple. Okay, or like this, the triple. If you look at just 1 carbon, I've got 1 single here, I've got a triple here. So what's the shape? Ignoring that guy, what's the shape? It's linear. Okay, so make sure you have kind of some notes on all this stuff. Any diatomic molecule obviously is also going to be linear because you only have 2 atoms. So a straight line between 2 things is the only possible shape. Okay, so then we get into triangular planar electron geometry. So I got 3 electron domains. Okay, if all of them are bonding, I get triangular planar. But what if one of them is not bonding? Okay, what if one of them, oops, that's too many. What if one of them, take this stick away. Okay, what do I have now? So even though there is a pair of electrons there, the shape of the actual bonds is a little bit different. So that's what we're looking at now. So triangular planar if you have 3 bonds, or bent if you only have 2 bonds. And remember that when we're talking about bonds, it could be a single and a double. Okay, so like CH2O. Okay. All right, so a little bit more triangular, planar, and linear stuff. These are literally pictures from your textbook. So all I did is kind of put them in here to summarize. So again, you're seeing examples, how many bonding domains, how many non-bonding domains, that's the stuff you've got to think about. If we go on to our famous tetrahedral shape, you know, methane, CH4 was always the one we used before, but remember that you can have lone pairs, you can have double and triple bonds. So remember that once we hit group 4 on the periodic table, once we hit the carbon group on the periodic table, you've got 4 electron domains on the atoms that we're typically looking at. Nitrogen, NH3, has 4 domains, but one of them is non-bonding. So that's where the lone pair ideas come in. So total of 4 domains, but how many of them are non-bonding domains? That's what's going to change the shape. So you've got the triangular or trigonal pyramid, or you've got the bent if you have just water, and I know this doesn't look like water, we're usually seeing white and red, but 2 non-bonding, 2 bonding, so a total of 4 domains, but just 2 bonding domains. Or something like HCl, which is linear, because 3 of them are non-bonding. And again, I don't have one of those here because it's simple enough. Okay, so if I have a tetrahedral, 4 bonding domains, if I take one of those bonding domains away and make it a lone pair, I get pyramidal. If I take another one of those domains away, now I get bent. And remember that a double or a triple bond is going to change things a little bit. Okay, so if you look at this one, here's carbon in the center, 4 domains, but I've got 1 that's a double bond, so it really counts as 1 domain. So 1, 2, 3 domains takes me to triangular, or it takes me to bent. So you got to worry about how many total bonds and how many non-bonding. So non-bonding pairs of electrons take up more room than bonding pairs of electrons. So what's going to happen as you go from a tetrahedral to a trigonal bipyramidal, no, to a triangular pyramid to a bent, is the angle's going to change a little bit, okay? Because those non-bonding pairs are going to cause the bonds to bend down. So the bond angle is actually going to be smaller. So here's what we're talking about. And again, all of this stuff is in your book. 109.5 for a true tetrahedral. If you have one lone pair, it's going to squish these other three a little more closely to make it 107. Second lone pair is going to squish those remaining two together even more to give you 4.5. Now, I've never seen AP want you to remember what the actual numbers of the angles are, but knowing that the angle is decreased with every lone pair that's around the atom is really important to remember. So when we want to find the molecular geometry, remember that it's the lone pairs that are going to contribute to where the atoms are located, but they don't appear in the molecular geometry. So find the electron geometry first, then figure out the molecular geometry based on the number of actual bonding domains. Again, back to book references, you've seen enough of these already that I'm going to kind of just zip through. Tetrahedral, trigonal, pyramidal, and bent. Trigonal, triangular, they use both of those terms.